So this is about the Carson's rule. So under case 1, that is for a single tone message signal, there are two different ways of finding the transmission bandwidth. So first one is using Carson's rule. The second one is using universal curve. Okay. Now you hope you have understood the Carson's rule. Second one is universal curve. That is universal curve. So what is this universal curve is? Look at this. So actually the Carson's rule will not give you the exact the bandwidth. It will actually underestimate the bandwidth of your FM wave. For more accurate measurement of bandwidth, you need to go for the universal curve. So here, look at this figure. This is one example wherein beta is equal to 1. This is the spectrum. So here, how many frequency components you need to transmit? So this actually keeps continuing till infinity. So how many spectral components you will retain and transmit? That is the question. So by using universal curve, it is actually given by, that is the bandwidth is given by 2 into n max into Fm, where n max is the maximum value of n, which will satisfy that the Bessel function should be greater than 0.01. So I'll just simplify this and tell n max is the number of spectral components, that is these spectral components, for which the amplitude should be at least greater than 1% of your carrier frequency amplitude. That is, if this is your FC, so that is nothing but the middle one is FC. So the carrier frequency amplitude is this much. Okay. So you will have to transmit as many number of spectral components around this FC in such a way that those frequency, that is those spectral components should have an amplitude greater than or equal to 1% of this carrier signal, that is carrier frequency amplitude. Okay. So if you consider in that way, so you will get n max. Then if you multiply with Fm, you will get the bandwidth. So Fm is nothing but the difference between adjacent frequency components. So this Fm into n max and twice of that. So will give you the number of spectral components you are actually transmitting. So that actually gives you the bandwidth. Hope you have understood this. Now, what is this universal curve? This universal curve is actually obtained by plotting your bandwidth. Sorry, this is not visible. This is actually B by delta F, capital B by delta F. This B is nothing but this bandwidth. Okay, so this is a normalized bandwidth because you are dividing it by frequency deviation, and this is plotted for varied values of beta here. So this is your modulation index. So as beta increases, your bandwidth is coming down. So that is what you can understand from this. So if you know the values of beta and delta F, from this curve you can obtain the bandwidth. So this is the method of obtaining transmission bandwidth using universal curve. Okay. So next thing is for an arbitrary message signal. So till now, I'll just go back. Under case 1, we studied about determination of transmission bandwidth for a single tone message signal. That is case 1. Now coming to case 2, wherein you will be observing a message signal which is an arbitrary. That means which may have a series of frequency components, several frequency components. So in that case, m of t is your message signal, and this is general equation which this we have taken from the property 2, that is wideband FM. S of t is given by AC into Bessel function into cos term. So bandwidth of such an FM wave, which is for an arbitrary message signal, is given by 2 delta F plus 2W. Okay. So look at this. This is also Carson's rule. 2 into frequency deviation plus 2W. So what is this W? W is nothing but maximum frequency component in that message signal M of t. Okay. As I have already explained, the message signal may consist of several frequency components F1, F2, F3, F4. Say for example, F4 is the highest frequency among all those four. Then this W will be equal to F4. Okay. And this is nothing but the maximum frequency deviation. 2 delta F is here is maximum frequency deviation. That is with respect to that maximum amplitude. So this is the difference between an arbitrary message signal and the single tone message signal. Here frequency deviation is just 1 and FM is only 1 because it contains only one frequency components. But if you use this Carson's rule for an arbitrary message signal, you should take the highest out of all those frequency components. We call it as W instead of FM, and the highest frequency deviation, that is the maximum frequency deviation, we call it as delta F here. Okay, this is also Carson's rule. If you take 2 delta F common, you will get 2 delta F into 1 plus 1 by D. So what is this D? D is nothing but we call here D as deviation ratio. Okay, D is equal to maximum frequency deviation divided by maximum modulating frequency. It is just like your modulation index. We can recall what is beta. Modulation index is delta F by Fn. Okay, but here when you consider the message signal as an arbitrary message signal M of t, then we call this as deviation ratio. So deviation ratio becomes the ratio of maximum frequency deviation to the maximum modulating frequency. Okay, so this is nothing but your D. So this completes the transmission bandwidth of FM waves. So there are two methods. One is using Carson's rule. The second one is using universal curve. Here also universal curve can be used to obtain the bandwidth. So whatever I have shown here is only Carson's rule. Next we will move on to generation of FM waves. Okay, before I start with generation of FM waves, we'll just go through one problem here, that is a numerical. Look at this. This is a problem on deviation ratio. So the problem, example 3, numerical. It says that in North America, if maximum frequency deviation is 75 kilohertz and the maximum audio frequency is 15 kilohertz, determine the transmission bandwidth of FM. So first identify what are the given data. So maximum frequency deviation is 75 kilohertz because it is here they are talking about an arbitrary message signal. Okay, so it is not single tone, so therefore you have to go for capital D here instead of beta. So D is the ratio of maximum delta F by maximum FM. So 75 kilo by 15 kilo if you do, so this ratio will give you 5. So this is nothing but deviation ratio. So when once you obtain deviation ratio, you can obtain, that is you can find bandwidth by using this formula which I have already explained. This is given by 2 delta F into 1 plus 1 by D. So 2 into 75 kilo. So this is nothing but the 70, that is the deviation which is given. plus 1, sorry, into 1 plus 1 by 5, that is D obtained from here. If you substitute, you will get the bandwidth. So this is nothing but using Carson's rule. So if you have to determine the bandwidth using universal curve, you will have to go back to that curve which I showed here. So using this curve, you can determine the bandwidth. How? I'll show now. So using the universal curve, for the given value of beta, that is 5. So beta is nothing but D here. So you have obtained this D as 5. So you have along x-axis, you just go to 5, that is beta equal to 5. For 5, what is the value of B by delta F? Look at this. For 5 as beta, what is the value of B by delta F? Here you have to pick the exact value. So that is nothing but 3.2. Okay. So to do this problem in this way, you need to have that universal curve. Otherwise, you cannot find this. So for beta equals 5, you have B by delta F equal to 3.2. So then if B by delta F is equal to 3.2, bandwidth will be equal to 3.2 into delta F. So delta F is known. If you substitute for delta F, you will get 240 kilohertz. So now you can compare this bandwidth obtained using universal curve with this bandwidth obtained using Carson's rule. So this is 180 kilohertz and this is 240. So as I have already told, Carson's rule will underestimate the bandwidth. Okay, so the more accurate bandwidth can be obtained by using universal curve. So actually we require 240 kilohertz to transmit this particular audio signal. Okay, so you have to use universal curve. So whether it is asked or not, you have to find it in both ways. If at all universal curve is not given, you can just end it here. Okay. Now coming back to the generation of FM waves. So how to generate this FM waves? So during initial classes, I hope you can recall the simple block diagram which we had used to generate FM wave. So that we call it as indirect method, wherein we will be using phase modulation. Just a minute, I'll just open. Okay, look at this. So this is nothing but generation of FM wave using phase modulation. First, you will feed the message signal to an integrator. So the integrated version is then given to a phase modulator, which is also supplied with a carrier signal. So this integrated version of message signal will modulate the phase of this carrier signal to generate a wave. That is going to be your FM wave. Hope you remember this. Now, that is your generation of FM waves. So there are two methods, indirect and direct method. The indirect method is the one which I explained just now. The direct method I'll be explaining later. So the block diagram of indirect method in detail is as shown. It consists of integrator followed by a phase modulator. So how do you do phase modulation? Is actually by using a product modulator, a phase shifter along with an adder. Okay, these three components you require to do phase modulation. So your integrated version of message signal will be undergoing phase, that is it will modulate the phase of this carrier wave to generate a narrowband FM wave. Look at this. This is your carrier wave signal. To generate this, you require an oscillator.